Let's see. There's a handout up front here for you. Okay, so we finished up regression last week, and we started moving on to a new topic, which was HMMs, hidden Markov models. Before we did hidden Markov models, we started talking about just Markov chains. And just as a reminder, I seem really loud here. As a reminder, a Markov chain is just basically a set of random variables. We're going to only consider the discrete case. So you have some set of random variables, or rather a random variable that can take various settings. So let's just say it's 1, ... up to 5. And then a Markov chain is a set, is sort of a sample of those random variable states over time. So you might have some x1, x2, ... and x up to x10, let's say. And those are, each one of those x's is going to be a sample from that set 1 to 5. Now, the thing about a Markov chain is you only ever look back, to find the probability of the chain, you only ever look back one step. So in order for it to be a Markov chain, the x at time I plus 1 is only dependent on the x at time I. So you only ever look back a single step. Now these are often, a Markov chain will often be drawn as a set of circles, where each one of these is a transition. And then you have sort of this x1, x2, x3 sort of thing, where it's showing the x's that you actually saw. And then this would be the probability to go from sort of whatever x equal to, let's see, x2, given that x was equal to x1, sort of thing. So it's this sort of chain of probabilities. So it's often drawn like that. It just, even if you don't put the exact values for the x1, x2, x3, you'll often draw the chains just to sort of show the structure. Now we talked about how, here it's saying that you can only look back a single step. That's not always that useful. So in something like language generation, you might want to look back, several letters or several words in order to do sort of a generation of some text. When you do that, that's a legal thing to do. You just consider your X symbols as sort of this superset, which is like 3 symbols. 3 words might become 1 symbol. So you just kind of concatenate the individual words into a single symbol. So you just play some games rearranging the probabilities and what you call a state in order to look back multiple steps. However, even though a Markov chain is defined like that, you'll often see drawings like this. Where this is basically, the arrows basically are saying there's some dependence, and you'll see something like that sometimes. And that's just indicating that sometimes you're looking back 2 steps. Again, it's still a Markov chain. We just need to, redefine what a symbol is in order to, redraw it without those skip connections in there. So if you see one of those, that's just indicating that they're kind of looking back more than one symbol. Now we talked about some different definitions. A unigram model is typically something where you don't look back at all. You just have the probability of x without looking back a single step. A bigram model, you're typically looking back 2 steps. Did anybody come in late? There's a couple handouts. Could you raise your hand if you came in late? Do you got him? And then there's, here you go. Oh, that's 2 of them, but I could be wrong. I guess this is a good way to count how many people come. Did you get one already? You don't have one? Okay. I think we got one more. Okay. And you need one? I think we might have trouble. I assumed that we never had more than. Oh no, we got one more. You got lucky. Now we're in trouble. So the last person in gets to draw it by hand, I guess. Okay, good to know we have over 20 people who come every day. Okay, so there is a handout. You came in late, so we ran out. It's in the book. It was taken directly from the book. It's just that if you're taking notes, it's going to be hard to draw it quick enough. So I didn't want you guys to be sitting there waiting, drawing it. Okay, so like I was saying, if you look back 1 step, that's usually considered a bigram model. If you look back 2 steps, that's called a trigram model. Again, the sort of things that we're talking about is, say we're talking about letters, then we're looking at sequences of letters. If you look back 1 letter into your sentence, that's a bigram model. But you could also consider words as your unit, and so the same thing happens. If you look back 1 word when you're generating a sentence, that's a bigram model. That sort of thing is kind of what a Markov chain is. Now Markov chains are useful to sort of generate text. So if you have some string of text, you can sample from the probability distribution to find another word and another word, or another letter and another letter. So they're kind of there's actually a lot of uses for Markov chains that we're not going to talk about. They're a very common probabilistic structure. But for our purposes, they're mostly used to, sort of generate text. We actually won't, they're just sort of a basis for what we're going to do, which is HMMs. So we won't really talk about anything more about Markov chains. Now, Markov chains are good to generate things, but you might want to, say, do something else. One of the things you might want to do is, say, recover text. So if we have the cat sat, why that's a common example in papers, I'm not sure, but this is a real common example. It's some text. Now, if we go through a noisy process, that text might get garbled. So let's say we send it over some transmission, and this becomes an F, this becomes a C, and I don't know, you get a B here. So you might want to recover that. That original sentence from your garbled sentence. So an HMM is something where it deals with a sequence of things. First of all, it's not like regression or classification that we've looked at. It's definitely for sequences, and it has a hidden state in it. That's why it's called a hidden Markov model. So here, this would be the hidden state that you wanted to recover. This would be your observations, what you actually saw. And so what we're going to do is we're going to make sort of a model where it's going to look something like this. There's going to be a sequence of variables, which we're going to call x's. And these are going to be the hidden variables. Hidden variables means you didn't observe them. So these x's correspond to the letters of the unobserved, the thing that we're trying to recover. And then there's something called the observed variables, which look like this. And the observed variables depend only on the hidden variable that's associated with them. So as you see there, the y, which are often called the emissions from the hidden state, they only depend on this, this x right here. So this is sort of, if you're going to try to recover this text, this becomes the emitted thing. This is the hidden state that you're looking at. And we're going to look at techniques where we're going to model this. We're going to model this probability, which we often call the probability of y given some x, is that guy. And this probability, which is the probability of some xi plus 1 given some xi, we'll model this HMM in that way. If we know these probabilities, this and this, we'll be able to say, we'll be able to find the most likely, given this observation, we'll be able to find the most likely hidden state that corresponds to that observation. So that's a real common use for HMMs. It's sort of recover something that's hidden that you know has some underlying process, and then use it, use what you observe to actually find the most likely hidden state. Now there's other uses of HMMs. Sometimes you just want to use them for sequence data. A real common old school usage that's not used that often anymore is something like speech recognition, where there's actually, you need to somehow model a sequence of the sounds that come out of, when we speak. And underneath that sequence of sounds, there's some sort of state that's sort of running that says, this is the sound that's going to come next. Now, we could kind of model that with a Markov chain, but they have found, at least old research, found it much more useful to model it with a sort of a hidden state back there that sort of told us what would be generated from this hidden state. And partly that's because just the way that speech is structured, and there's some repetition, and there's different things that are going on, that they found that that was pretty useful. So in that case, you really don't care what the x's are ever. All you care is that given a set of observations, you want to be able to say, with some, what is the probability of this observation being emitted? So there's this chain running in the background that's hidden. You don't care really what it is, but you can actually take the observations and find a probability of those observations based on that hidden chain. Another usage that you see out of HMMs would be something like where you want to sample sort of like from a Markov chain. If you want to sample like a sequence of actions, like if you had a person moving around and you wanted to have a person dance, you could set up an HMM that would sort of generate that, a sequence of moves that were somebody dancing. And there's some hidden state back there that's kind of driving how the next move is going to happen. So there's a lot of different things that can kind of go on here. So this is what we're going to be looking at. Let's look at the two examples I mentioned. So the first one is recovery of speech. So in this case, we're going to have a, let me zoom in a little bit. We have some text, and this text is the hidden state. This is what we don't know. This is what we want to recover. So what we can do is we can model the language that we know. What this example actually did is it took the text from this chapter and basically modeled the transitions. And so some of the transitions here, if we just look at unigrams and the most common things that happened in this chapter, star stands for space, just so it's not a big empty box. So you see spaces are the most common symbol in this text. Then followed by E, T, all the vowels. S and N are really common. R is a very common letter in English. So we can get this. Now we can use this unigram model, and we need to know, so this is basically the probabilities of the transitions. Now again, because we're using a unigram model, we're not actually looking at the past, which is kind of an odd thing. Now for this example, we also need to know what is the, given this X, which is a set of letters, what is the probability of getting a Y? So in this very contrived example, basically what we said is that with a 0.03, I don't know if it was 03% or 0.03 fraction, it's in the text. With some very small probability, we're going to, for each letter that is in the original text, we're going to emit a different letter. And that different letter is either going to be one ahead or one behind the actual letter. This is supposed to mimic old typewriters, and they had like a rotating head that had all the letters kind of around in a circle, and sometimes it'd be off by one. So this actually was a type of noise model that would happen. Now given this, we can also look at this is the bigram. So if we have a space, the chance of having the next letter be a T is this, an A is this, an I is this. So you can see these are kind of the first letters of words. If we're inside of a word and we have an E, E's are often the end of a word, so they're often followed by a space or an R or an S, and the same thing. And this is just like the top 10 most common things. And then we can look at the trigram model, which is, let's see, this is basically saying that after a space T, the most common thing was an H. After a TH, the most common thing is an E. After an HE, the most common thing was a space. You'd have a whole giant table for this. You know, that was 27, so 26 letters plus a space, so 27 symbols to the third power for the number of probabilities you have to build. So it gets pretty big pretty fast. So now, given that noise model, we can do inference, and we can recover the most common sequence that generated this. So again, we're trying to look for this original. The trellis has two crucial properties, blah, blah, blah. Down here, we can look at the unigram model. Where are the errors? Let's look at the errors just a second. The trellis has, oh, here we go. This is the noised version of it. So we took the original, we added noise with that. Here's the probability of adding the noise. So it wasn't percentage, it's actually the probability. And then here is the text that came out of doing this mess of stuff. So if we use the unigram model, we're basically going to be replacing some stuff. And I don't really know, actually, which ones got replaced properly. Pretty much nothing really gets done well. I guess there was one Z that got replaced, because that's a very uncommon letter, and it got replaced by a Y. So a unigram model we wouldn't expect to work real well. Here's a bigram model. For some reason, the became she. David actually thought that was probably an error in his calculations. That's a fairly unlikely thing. But what happened here is we did recover same text in, how many was wrong here? So there's 13 that were wrong, so plus 443 that were right. So now we're up to 449. If we go to the trigram model, now we're getting really good. I think the only mistake here is this guy, and I think it's only this guy. So we're only missing 2 letters. And again, this is just finding the most likely hidden state given the observations. So that's one real common use of the HMM. So like I said, another common use of an HMM was speech recognition back in the day. They're not used anymore. Everything's gone to neural nets. They were always kind of so-so even when they had them. But I wrote this yesterday. For what it's worth, I did this basically as my final project for my undergrad. We had a capstone, 1 semester long sort of thing. It took me a full semester to do what I did in about 3 hours yesterday, mostly because almost all of the tools exist out there. This is a meta point on this that I've mentioned before. This class is about teaching you how to use, it's teaching you what tools are available in ML, and you should not be writing those tools yourself. You should be going and finding them out somewhere. If you need to do text parsing, go find something that does the text parsing for you. If you need to do k-means, go find a k-means algorithm. Don't write it yourself. Even though we talk about how they're written, we talk about how they're constructed, we talk about the underlying theory to some extent, don't go and write this stuff. That is a mistake when you're doing machine learning. If you can't find one, okay, fine, write it. But mostly, all these algorithms are out there. True applied machine learning is not writing the algorithms. It's pipelining all the stuff together, which is exactly what I did here. So in a speech recognition system, basically you get a waveform, and then you got to learn what the specific word was or sentence was that you heard. And in this case, I just did digits. I didn't do sentences. Sentences get really complicated because you have to figure out where the sound boundaries are. It gets really fairly difficult. There's standard pre-processing that you do when you do speech recognition. So here's the waveform. This is what you actually get from just looking at the actual sound as it goes. This is a standard form of pre-processing called MEL frequency substrol coefficients. This sort of represents what our auditory system actually kind of pays attention to. So for each segment of time, and you sort of take discrete chunks of that original waveform, you get these sort of frequency bands that have some strength. So the white is a really low strength in that frequency band. The black is a really high strength. Given this, because we're only going to be talking about discrete states, we need a way to take what is basically a single step here, this step, which is composed of 26 real values, and we need to convert it into a single sort of discrete value. And so this right there comes in clustering. We saw this sort of technique when we did vector quantization. We built sort of a dictionary. We cut up our signals and we built a dictionary. It was so we could later build a fixed length feature vector. We're not going to do that here, but we did use the dictionary technique. So I took all of my data, I chopped it up, or I did this sort of thing, and then I clustered all of these individual layouts that came for all the speech signals. And so these are the clusters you get. Now they're random order, so you don't see any rhyme or reason here. But these are sort of representative of all the different things that I saw in my signals. This is, again, I only did 100 clusters. And I could do way more. You didn't really, probably 100 was overkill. These are probably a lot of similar ones and didn't need them. If we take this same signal and we push it through our dictionary, so we find the cluster that each of these time segments belong to, and then we map it to the cluster centers, this guy gets translated into this. So you see we actually lose a lot of information. And what we're actually going to work with is just each one of these has an index. This is index 7. cluster 7, this is cluster 3, this is cluster 5. Those are going to be our observations. So we're going to try to model this sequence using this set of discrete observations. So there's, at each step, there's 100 things you could have observed. And then you're going to have, each signal is going to have a variable length. So then what we do is we train an HMM for each individual word. In this case, we're just using the digits, so we get 10 HMMs. Again, there's a hidden state that's running out there that's going to be sort of moving along an X that you don't know, and at each X, it's going to emit one of these clusters. So we can kind of figure out what the probability of a speech waveform being each one of these words sort of matching each one of these HMMs that we created. So we created 10 HMMs, and here we can actually see after we created the HMMs, we get some train and test probabilities. I took 10% of the data. I think there was 2,000 utterances, so 200 of each digit, and there was I think 4 speakers, and so they said each word 50 times, that sort of thing. So you can actually see these do a pretty good job on the digits. Like we get 93% accuracy or so on recognizing digits on the test set, and then we get about 87. We can look at kind of how the probabilities came out. Again, we usually use log probabilities. Just because log probabilities, remember we're going to be talking about very small probabilities. When you have a chain of very small probabilities and then those chains are very long, your probabilities get very, very small. So these are the log probabilities that actually came out. The digits are, this over here is 0, this is probably this range, the next range is all 1s, these are all 2s. And you can actually see, I lost my legends here, but I'm not sure where those went off to. Did I make it too big? Ah, there we go. Here are my legends. So you can actually see the blue dots are represent the probability of it being a 0, the green dots with a probability of it being 1, that sort of thing. We talked a little bit a little while ago about doing softmax to sort of normalize if you have a bunch of probabilities. Basically, you take the exponential of your prediction over the sum of the exponentials of all the predictions, of all the different predicted values, and you can get a normalized value. And what you actually see here is the normalized value is for each of the classes is going to go from 0 to 1. And what you actually see here is it does really good on 0. It does okay on recognizing 1. There's a couple oddballs in here that it categorized as something else. 2 does pretty good. 3, there's a couple mistakes. Let's see. This guy is 1, 2, 0, 1, 2, 3, 4, 5, 6. 6 it does a really poor job on for some reason. I don't know why. 7, 8, and 9 it does a pretty good job on. So this is like I said, used to be a very common usage of HMMs. Theoretically, you could also sample from HMMs, just like you can. I was talking about dance maneuvers or positions that you can try to build up sort of a sequence, a common sequence. You could do that same thing for speech. It usually ends up as garbage. There's no reason that we can't sample from these HMMs and we could say, I want a 1, and it would generate a sequence that it finds highly probable of being a sound of a 1. For whatever reason, that doesn't actually come out to be very good. It would be highly probable, but there's a lot of long-term correlations it actually loses. All right, so those are two examples of HMMs. For what it's worth, like I said, I used all stock algorithms there. I found the pre-processing out on the internet. I used k-means. I used HMM from the internet. These are all Python packages that existed. all I did was glue them together with, to load the data. And loading the data came from a package, a lot of sklearn stuff. So again, don't write your own stuff. Just glue together other stuff. What's the question?
So you said HMMs are useful for when you have like basically these different states that you're transitioning to within the data elements as you read more data elements.
Mm-hmm.
Are your data elements like every single fragment in the every single like millisecond or wherever? You know how you have this speech of like someone saying one, is then like each data element the like little millisecond where?
No. What you actually do, and again, this is old speech processing took a lot of pre-processing. So this whole waveform gets chunked into, it looks like probably 19 parts or 18 parts. And then for each part, we run it through basically a fast Fourier transform, which sort of pulls out the frequencies that exist within that window. And then from then, we do this transformation that converts it into something that's known to be really good for speech recognition, basically. And that was all research from back in the 90s, sort of what a good sequence is. So this is actually the observed state. And then, like I said, I did discretization so that they're just basically integers for each one of these 19 steps. So this one, I think, this might have been this was a number 4. This was somebody saying 4. And this is the input that goes into HMM. Well, not even this. So this got chunked into, this signal got chunked into to 19 bits, then transformed and basically into the frequencies. Given those frequencies, we formed a dictionary and got back basically this. But what we're really using on the HMM is the indexes of the clusters, not this thing. Does that make sense?
Kind of. Okay, so basically you take this waveform and you run this fast Fourier transform so that way it extracts the most common frequencies?
Not the most. This guy has frequencies that make up this waveform. So any time series waveform can be converted into frequencies for small windows of it. So you take a small window, you find the frequencies that happen to basically the tones that are in that window, and you have to chunk it into a window because each chunk is probably 25 milliseconds or so. And over those 25 milliseconds, you're going to have a bunch of frequencies that occur in there with certain strengths. And you can reconstruct that. You can actually go both ways. If you had a bunch of frequencies, you can get a waveform out. If you have a bunch of waveforms, you can get the frequencies out, sort of thing. Make sense?
Yeah, okay. So then the frequency along with the label is the training data item.
Yep. Yeah, there's a separate HMM for each label, is basically the way you do it. So you get 10 separate HMMs, and then when you want to predict something, you basically go to each HMM and you say, what's the probability of this unknown sequence, of unlabeled sequence? It spits out a probability. The HMM that corresponds to 0 spits out a probability. The HMM that corresponds to 1 spits out a probability, that sort of thing. And that's what these guys are. Any given column is the set of probabilities that got emitted, and then this is just the normalized set. So like here, I think these guys, they're probably not in the same column, but like this guy has a bunch of them, this guy has a bunch of them that are non-zero. So you kind of do that. Make sense?
Yeah, so then also it's got to be, maybe like the runtime of classifying is order of the number of labels you have as well, right?
Yeah, so you don't do words in the end. You do phonemes. And there's only, like in English, there's only 26 phonemes, so you'd only have 26 models. But then you do have to do chaining. This is like the simplest, dumbest thing that you can do, and get, you You take discrete words that aren't chained into sentences. You model just the word. It's really simplistic. That's why I can do it in 3 hours. It gets really complicated when you, and this is why HMMs didn't work so well, is you have to start guessing where the phoneme boundaries are, and you have to model that, and then when you get a new signal, it kind of tells you the most likely phonemes, and then given those phonemes, you have to construct what words came out. So you often would do hierarchical HMMs where you have sounds mapped to phonemes, phonemes mapped to words, words mapped to sentences, and then you do sort of a joint probability over this big giant pyramid of stuff to do the recognition. So any individual bit was actually pretty small, but when you ended up doing it all, it got pretty complicated. Make sense? There's whole books on speech recognition. This is like state-of-the-art 1988. You know, like way back. It was published by at least 94, 96, something like that. This kind of stuff. So it was published in a book. So it had, you know, it was pretty common. All right, any other questions? Okay, my examples took a long time, so we're behind, but that's okay. I spent a couple hours, so you guys can spend a couple minutes looking at it. All right, so let's define this a little more formally. We're going to have a sequence of a set of sequences. This is just the model that I described. So you have some x's that are hidden, and again, it's a sequence of x's that occurred after each other. And so it's kind of a chain to x2, up to xn. And then each one of these is an emission. Given the state that this x is in, you get a y1, y2, up to yn. So that's kind of our structure of our model. These x's, each one of them follow the same probability, and that's p of x. I'm not sure why he switched to u's here or switched how he numbered them. But if u was the time step, the x at this given time step, the hidden value is only dependent on the one before. This first one actually has a probability. You need a separate probability of just x1, just because nothing came before it. So you need sort of a prior without knowing what came before, because nothing came before. And then we're going to have a second set of probabilities, or a second distribution over the y values given the x values. So this is just the probability of this observation given this state. So those are the 2 or 3 distributions we need in order to model an HMM. Now, one of the things we often want to do is, given a sequence, y1 down to yn, we want to recover the x1 to xn. Now this is sort of the situation where we're trying to recover the text, where we kind of have the states mean something. So we want to recover that hidden state. So we can model this. The probability of a sequence x1 to xn, given the observations that we saw, that's what the probability would look like. And we can, if we just go over all possible sequences, basically find the maximum of this, we can get what the probability is, what the most likely recovered probability is. So if we're going to maximize this typically, now this we can take, we can do a little transformation. We can find the joint of x1 to xn, y1 to yn, and there's a normalizing factor of the likelihood of the observed sequence, probability of y1 to yn. Because we're going to do a max, and we know the y1 to yn, we'll often ignore this term down here. That's often ignored. Again, the max isn't modified. You know, we're trying to find the max over the x sequences, so it doesn't matter what that normalizing factor is down below. So really, we're going to look for just this guy. I hope we get to our handouts. Otherwise you guys have to bring them back on Thursday. I think we will. Oh, we got plenty of time. We're going to look at the. We typically look at the negative log probability of the x sequence, y sequence. There's one end. And this is going to be equal to, remember we have a bunch of independents. Given x n, we know we got the probability of y is independent of everything else. And given the one step back in time, the probability of an x is independent of everything else. So we can rewrite this. Again, because we're taking the log, we basically change the product to a sum, and we come up with something that looks like there's a negative in front of this whole thing. We come up with the log of basically observing the first state plus the log of being in the first state plus the log of observing the first y given the first state that we see. And then this starts just repeating. This is the log of the probability of x2 given x1 plus the log of the probability of y2 given x2. And that just goes up to the log of the probability of seeing xn given xn minus 1 plus the log of the probability of yn given xn. So that's sort of the equation for the joint probability. Does that make sense? Any questions on that? All we did was take the joint probability, take all the independence assumptions that we basically are enforcing on the HMM, and this is what we come back with. Now, when we take the maximum, we're taking the maximum over all possible sequences of x. So there's going to be an exponential number of sequences of x. So if we're talking about letters and a space, we have 27 symbols that x can take. And then we're going to have, let's just say our observed sentence is 10 characters long. Then we're going to have 27 to the 10th. We're going to have this giant possible set of x's that we'd have to check. The nice thing is that because of the structure that we showed before, a sequence looks something like this. Because we only have to ever look back in time, we can do something really sort of fancy where we treat this as sort of its own sequence, and then we find the best path out of there, and from there we kind of find the best path out of there, And so we do this sort of look back each time where we take the very end of the sequence, then we take the sequence of 2 and a sequence of 3, working from the back. And this actually is very efficient. We can do this in polynomial time to find the highest probability, the maximum, the maximum value for your path. And we're going to look at that algorithm right now, and that's actually why you've got those pieces of paper, because we're going to end up unrolling sort of this network in various ways. We're going to use dynamic programming for what it's worth. This is just a dynamic program. A lot of you have probably taken the dynamic programming class. I think it's a 400 level class, 437, I don't know, something like that. I don't know, I don't teach for dynamic programming. But that's what this is. It's a dynamic program that, because of the structure, we can do it very efficiently. If we did it sort of like naive recursion, we'd have this giant recursion that we'd have to do, so we could kind of do different things. Got a question?
It's also 374.
374.
But anyway, I was wondering, conceptually, like, what do I know that the nodes on the bottom are the emitted things, and the nodes on the top are the hidden
Yep.
states. So, like, what does the state represent? Does that represent a word or character that would...
It depends totally on how you define this. So when we're doing letters, X takes the set of A through Z and space. So that's your set of hidden symbols. It also happens to be your set of emitted symbols. A through Z and space. So when we're doing sort of reconstruction of text, those are what the values are. And then there's a probability for each. So for a bigram model, there's a probability of going to A to B, A to C. There's a probability of B to A, B to C, B to B, B to C, that sort of thing. And then there's a probability that if you're in X, you emit, if X is equal to A at time 1, you emit an A at time 1, meaning that Y is equal to time 1. So that's the kind of thing that these states and the observations would take. Now with speech, you only know the observations. The states have some hidden meaning or unknown meaning that you don't even care about most of the time. So like in my HMMs, I used 50 states. What they mapped to, I don't know. I took 100, I had 100, 50 was probably way overkill. I probably could have done it with way less. And I had 100 clusters, so there was 100, basically Y was 100, basically 0 to 99. Each segment got assigned that. Which were basically the cluster numbers. And then the states, there was 50 of them. I don't know what they map to. We don't care about the hidden state. We just care about the probability of the observation at that point. So we would figure out the probability, the maximum probability of that observation, and then just not even care about what the generated, we could recover the most likely regenerated hidden states, but they have no meaning. They're just something. And often you'll have that. You'll have some hidden state that you just don't care what it is. The models sort of build their own meaning of what those hidden states are. Basically, hidden state 1 means generate this kind of stuff. Hidden state 2 means generate this kind of stuff. So you don't really care what it is. You just care about the probability overall. Does that make sense? Okay. All right, so we have 3 different state diagrams we'll often look at. This is often called a sequence model. It shows how you kind of lay out the sequence of things. It's also labeled often as a graphical model. A graphical model is sort of the superset of this is how things are chained together. And so we'll often talk about them in this, we'll call this kind of model like this. There's another type of diagram that we're going to draw, which is a state diagram. And a state diagram is just a finite autonoma sort of diagram where you're seeing how we move between states. So you actually have an example on your piece of paper, if you happen to get a piece of paper. Right here, this is a state diagram. And what this is saying is, if I augment this a little bit, is that if I'm in state X and it has a value of 1, I'm going to move from this state to this state with some probability. So this probability is the probability of going from some x at time I equal to 1, given, let's see, I'm going, wait, that's a 2, at xi minus 1 equals 1. So basically, if I'm in state 1, what's the probability of going to state 2? So, and the same thing, if I'm in state 2, what's the probability of going from state 2 to state 3? So this represents just the transitions among the x's. You could assign emission probabilities to each one of these things, sort of when you arrive, what is the probability of emitting something. Sometimes that's drawn kind of like you have a little thing like this maybe, or dotted lines. Generally those don't get put in there, but that's just sort of if you wanted to include your y's into the state diagram. Those are a little less common to draw on a state diagram. And then this last one is called a trellis. And we're going to talk right now about what a trellis is. This is what's going to allow us to do a dynamic program to solve this in sort of polynomial time instead of exponential time. So basically what we did here is we unrolled a sequence of an HMM. So each one of these columns is a time step. So this is sort of, as we go from here to here, that's time. And again, we're talking about discrete time. At each time step, we can be in a certain state. So these are the x's, x1 would be equal to 1, x1 would be equal to 2, x1 would be equal to 3. So in this case, x can take the values of 1, 2, 3. And that's the same thing. That's that the state diagram there is showing. We have 3 x states, and we can move among them. This guy, each one of these things also has a probability associated with it, which is the emission probability. So for this node, we're going to have the emission probability of, it's at y equal 1 because it's time 1, and we're talking about, again, time 1, x1, is equal to this. This one, the emission probability is, again, we're at time 1, so we're in column 1 here. We're, again, time 1, and the state we're talking about is state x equals 2. And then this guy, not sure why this wasn't labeled, but this guy, just to make it explicit, is going to be the probability of the y2 value given the x2 value is equal to 1. And then this is the probability of y2 given x2 is equal to 2 and 3. Does that make sense so far? So we have each node in this diagram corresponds to an emission and a state. A probability, it corresponds to the state of x at a certain time. So you get them all, and there's a probability associated with the emission that came out of it. So you can see we kind of unrolled all possible states there for time 0, or sorry, time 1. Now the arrows are basically the possible transitions from one state to the next. So if you look at our state diagram, if you're in state 1, you can only go to state 2. If you're in state 2, you can only go to state 3. If you're in state 3, or sorry, let me go back. If you're in state 1, you can go to state 2 or to state 3. They're the outbound arrows. If you're in 2, you can only go to 3. If you're in 3, you can only go to 1. So that is the sort of the state diagram, how you can move around between x's. And so when you draw this trellis diagram, you add edges basically that are the possible transitions from between states. So from 1, you can go to either 2 or 3. So you can go either there or there. And associated with that edge is the probability of going from here and the probability of going from here to here. So you can see there's 2 edges, 1 to 2, 1 to 3. And then from 2, you can only go to 3, and from 3, you can only go to 1. And then that's just repeated over and over again. Now, the one thing that's left off of here is that initial probability of being in any given state. I'm not sure why that was left off. You can kind of think of there is an arrow going into these states that is the probability of x1 equaling 3. So basically the probability of getting to that state on the very first step. You don't have any history before that, so you have this sort of probability that isn't conditioned on anything. Those aren't drawn. They only go in to a single state. You know, there's nothing, they're not going between each other. So that gives you kind of a feel of how this all goes together. Now, the nice thing about a trellis is that, first of all, it's going to make it so we can efficiently calculate this. But you can actually look at any given path and figure out what the probabilities are just by adding all the probabilities along the path together. So if I wanted to know the probability of going from 3 to 1 to 2 to 3 as a sequence, given this y sequence, all I would do is add together the probability of starting in 3, the probability of this emission given state 3, the probability of going from 3 to 1, and then repeat. You know, this probability, this probability, this probability, this probability, this probability. So you just add them up. Any path you take, you just add up the probabilities. So if you want to know a specific x and for a specific y, that's really easy to recover the overall probability of that particular thing. Of course, that's not what we want to know, really. We want to know the maximum, the most likely path that you would take. And that's what we're going to try to talk about in the next 15 minutes. So the way this is going to work is we're going to work from the back, and at each step, we're going to find the most likely path after that given time. And we're going to call this the sort of the best path leading the node, or the cost to go to. That's an odd phrase. I don't know that that's a standard phrase, but it's sort of the cost to leave this. So we kind of ignore this last step just because of how we're going to do it. And what we're going to look at is when we're at this time 3, we're going to consider the cost to go. So what is the cost at time 3? What is the cost to go from this state to this state, and then follow the best path after that, the minimum path after that? And then if we're here, we're going to we're going to say, what's the cost to go from 1 to 2? So it would be this probability, and then follow the best path out of 2 to the end of the sequence. So I don't know what the only path out of 2 happens to be this one. The cost to go for this path is this probability plus this probability plus the cost to go from 3 to the end. So the cost to go is always the best cost in the end. Sorry. The cost to go is when you're leaving a node, take that particular thing and then follow the best path after that. Given the cost to go value for leaving a node, we can always find the best path out of a node. So if we calculated the cost to go of this guy, and we calculated the cost to go of this guy, the best path would just be the minimum of those two. The maximum on this diagram. Typically we use the negative log likelihoods here, or technically we use the negative log probabilities, in which case you do the minimums. So basically for this node, you would come up with the best path that leaves that node, and it would have an associated cost. Does that make sense so far? Any questions about that? This stuff gets really hard to kind of look at. And you have to be very careful when you set up a dynamic programming to kind of be clear what cost is, what probabilities or what costs are included at what points. So when we talk about the cost to go or the cost of the best path, we're only talking about this cost onwards. Or if you're talking about the best, you're talking about maybe the minimum of these two onwards. We don't consider the cost of this node when we talk about the best path leaving it. And that's why we talk about cost to go from a particular node, but we don't consider the cost of that particular node. It's just the way we define it. We don't include this cost, the cost of the emission of this node. When we talk about cost to go, we're just talking about the cost of everything leaving that node and beyond. So cost to go is a specific way to leave. Best path is the cost to go of the best path. We could define it the other way. We could consider that in the cost, the cost of that node. It's just you're changing nothing in the calculations. You're just changing the all you're doing is changing sort of the way you look at it. And when you define a dynamic programming, or when you define regression for that matter, you have to keep this stuff very clear, what you're including where, so that you don't double count something or you don't set up the math incorrectly. That's the hardest part of setting up a dynamic programming, is sort of building the trellis out of the dynamic program and making sure that you think about how you're transitioning through the dynamic program. So let's go through an example. That's what this guy is. We should have just enough time to go through an example. So we came up with a really simple example. If we look back really quick here, this is the state diagram we're using. The transitions are from 1. You can only go to you can go to 2 or 3, and we're going to do that with probability 0.5 for each of them. So there's going to be even probability of leaving 1 and going to 2 or going to 3. And then obviously, since there's only one state for the other ones, these are both equal to 1. You always take that particular edge. The probabilities of y given x equal to, xi equal to 1, sorry, the log probability, the negative log probability, is going to always equal negative 1. So it actually doesn't depend on the y here, which normally it would. This is just for simplicity. We're going to basically ignore what it was emitted. we don't care what was emitted. Normally, the probabilities would change depending on the time step, the y that was emitted. But what this is showing is that this particular node has a value of -1, -1, -1, -1. So anytime you go through that node, you're going to have a -1 coming in. The first thing we do in the dynamic program is we basically look at this last row, and we can basically ignore it. These are terminal states, so there is no cost to go going out of them. So there's no value leaving them. So there's nothing there. So really what we do is we start here. And we start calculating the cost to go for each of these edges. So the cost to go, the only way that we can leave state 1 at time, this is time 1, 2, 3, 4. So at time 3, the only way we can leave is this way. So obviously this is going to be our best path. The cost to go is going to be equal to the cost of arriving at the node and the cost of taking the path. So, sorry, I lied. There's actually a separate, you can go from 1 to 3 also. So let's look at both of these. This happens to be the best path, but we can look at both of these. So the cost to go this path is equal to the cost of taking that particular path, which is equal to, let's see, the probability of going from 1 to 2 is equal to 0.5. So the log of that probability is equal to negative 6.69. So you take the cost to go, or the cost of taking that path, which is 0.69, and you take the cost of arriving at that node, which is -3. And so the cost of going down this route would be -3.69. The cost of going down this dotted line, which we didn't take, would be the cost of going, again, this route, which is -0.69, plus the cost of arriving at this particular location, which is -9. So the cost of this guy is -9.69, or blah, 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 as I wrote it. So that's why when we consider the best node out of here, this is the best one. We didn't actually take the negative log probabilities in this diagram. Usually you would. So we have to take the maximum, not the minimum. So these are just the log probabilities. So we're going to take the max, which is -6.9. Now we do the same thing for each of these. Now these guys are a little easier because you can only take one route. So the cost of going down this line is always going to be 0. The cost of arriving at 3 is going to be -9, this guy. Same thing, going this guy is going to be from 3, oh, it's right here. There's 0 cost to take that path, and then arriving at 1 is a -1. Now we take a step back. We know our optimal, basically best path cost of going forward here. So now we're going to calculate this guy, the next one back. So again, we are going to take an exit. So there's actually 2 exits here that we could have taken. The bigger one is the maximum one is this one. So it's the probability of this, which is again 0.69, and then you have to add the cost of hitting this node. So that's 9. So now we're at 0.69 plus 9. And then the cost of the cost to go of this particular node, so everything beyond that, the best, basically the best path, which we figured out right here. This is the best path leaving this node. So it's 0.69 plus 9 because we're going through this node, plus the cost of the best path, which is -1. So that becomes -10. You could do the same thing for this dotted line. It just comes out to something worse. We do that for each of the states. We get a -10 and a -469. Then we go back one more. We would figure out that we would take the cost of this transition, which is 0.69, the cost of hitting 2, which is -3, and then the cost of basically the best path out of 2 is -10. So 0.69 plus 3 plus 10 is equal to -13.69. Now again, when you do the final step, you have to get the final score, you have to consider this node, what the cost, because we've only been talking about the cost beyond this node so far. This is the cost of exiting this. So the final score you have to talk about, you have to consider this particular cost also, which is 1 for this guy. So you go from 13.69 to leave, you subtract 1 and you get 14.69. Left out of this is actually the cost of entering that node in the first place, which is that, again, that probability of just x by itself. I'm not sure why he left that out of these diagrams. It's a little odd that that's not in there. Normally, you'd have a cost to enter into that node in the first place. But given this dynamic program, we can now see that a couple things. This is the best path. It's the maximum path. And if we just traced back through our logic, we can actually see that the best path goes from 1 to 2, 2 to 3, 3 to 1. And so that's the dynamic program we're going to run. On Thursday, we will run through the math a little bit and talk a little bit more about this. But that is the idea. If you didn't follow this, you should go through the book and try to work the example yourself. This is an important concept. It gets a little slippery at times. So it's a little hard to track all the pieces. So you should do it just to make sure you can do it. Is there any questions before we go? All right, cool. See you guys on Thursday.